So yeah, 24 is right. Hydrogen has 1 valence electron. Carbon has 4 valence electrons. 3 oxygens, each oxygen 6, so it's 18. And then the -1 charge, which is an extra electron, is 24 electrons total. Okay, then you come up with a skeleton. Did somebody come up with a skeleton structure? A lot of people like symmetry. I like symmetry too. So maybe something like this. They're very symmetrical. Does that look good? No, why not? Yeah. We have to talk. There's something we need when we're dealing with Lewis structures, and we need something called formal charge. So let's talk about that because this is going to help us get the correct skeleton. When we do this following the rules, what we'll do is complete the octets to the outermost electrons. So that's 8, 16. This is 24, 26. 26, I don't have 26 electrons, so I'm going to get rid of 2 of these electrons. Keep them paired up. I don't want to have a single and a single. You know, a single and a single is unstable. Do you know when you have a single electron like that, like here, a single electron, this is called a dangling bond, or a free radical or radical. Radicals are not stable, you know, they want to bond to something. And so I don't want to leave it like that. And so what I'll do is I'm not going to make 2 free radicals because that's going to be unstable. So I'll have it paired and then this one's going to be short. So it takes care of 24 electrons. This oxygen, unfortunately, doesn't have an octet, but there's nothing we can do. You know, we can't form a multiple bond, really, because that would give carbon more than an octet. And carbon doesn't get more than an octet. But the key here is this structure does not look good because the octet's missing, plus the formal charges are all screwed up. Because if we look at the formal charge, this has a negative formal charge, this has a negative formal charge, and this has a positive formal charge. The formal charge, what was formal charge again? Did we talk about formal charges earlier? A little bit? We're talking about oxidation state. This is not good because, you know, when you look at the charges, this oxygen came out short. This oxygen came out ahead. If we have a tug of war between 2 oxygens, which one wins? Well, it should come out as a tie, right? And so this is unstable. You know, one oxygen loses, the other oxygen gains. And so when I look at that, that doesn't look good. This looks unstable. Okay, so it's unstable because of the formal charge, and it's unstable because we don't have an octet. So the formal charge and the octet are both screwed up on this. And there's nothing we can do to fix it. And so formal charge, you know, can quickly tell you if a structure, a particular structure doesn't look good or does look good. There are other clues that this is not so good either. Another clue is this is supposed to be an acidic hydrogen. Bicarbonate is acidic. When I think about it, hydrogen bonded to carbon, is a hydrogen bonded to a carbon very acidic? So for example, if I have methane, is methane good at neutralizing bases? No. And so this is another problem here because it's an acidic hydrogen bonded to carbon. It's not good. We know that this is acidic. Now what is acid? You know, acid is this. Acid is H+, right? And so the more positive that hydrogen is, the more acidic it should be. Well, this, is this very polar here? Is this a very positive H? No. Because when we look at this, if we're looking at the delta plus on here, the delta plus is so small, it's negligible. Right? In fact, this is what we call a nonpolar bond. Nonpolar bond, actually an ideal nonpolar bond would just be 0 and 0 of the charge. And so for acidic hydrogens, we always bond the acidic hydrogen to the most electronegative element present. And so bond to the most electronegative atom. In this case, it's not carbon, it's going to be oxygen. And so there are a number of problems that we see with this structure. Even though it looks nice and symmetric, it's not a good stable structure. This structure is actually quite bad. We could do other structures, for example, like this. Maybe not so symmetric, but how about that structure? So there's another problem with this structure, and that is this bond here, an oxygen-oxygen link. This is called a peroxide bond. One thing about peroxide bonds is they're very unstable. They're extremely weak. And so we try to avoid forming these. They're weak. You can form them, you know, like a hydrogen peroxide. Hydrogen peroxide you can buy at the supermarket, wherever. But hydrogen peroxide is very unstable in the sense that visible light has enough energy to break this bond. And so hydrogen peroxide, you try to minimize exposure to light, otherwise you'll decompose it. And so if we can avoid forming a peroxide bond, it's better to avoid it. So we don't want a skeleton like that. Plus, the formal charges on this structure are going to be way off. And so what we end up with is a structure like this, maybe, in which the hydrogen will be bonded to one of these oxygens. Here we don't have any peroxide bonds. Another thing is, we like to keep the least electronegative element in the center. Yeah. Or the biggest. You know, the biggest or the least electronegative in the center. Okay, now this looks okay, and then we can complete the octets to the outer electrons here. Like that. Well, that takes care of 24 electrons, so this is good. This checks out. But there's a problem with this structure. What's the problem? The carbon doesn't have an octet. And so we can make an octet. The way we make an octet is just drop a lone pair into a bond. So you just pick any of these lone pairs, this for example. If we do that, then we can get an octet here. Okay, then we want to look at the formal charges. You guys remember how to count formal charge? No. Yeah, the formal charges, well, let's talk about formal charges here. When we say formal charge, oxidation state, and bond polarity. The formal charge makes an assumption. It assumes 100% covalent. Oxidation state assumes 100% ionic. Bond polarity is tries to come up with a more accurate value for this. More accurate value for charge. Let's do something simple for this. Water. Look at water. Can you do the oxidation states of water in your head? What's oxygen? -2. Hydrogen? Why? Because when we do oxidation states, winner take all. Oxygen is more electronegative, it takes all the electrons, and therefore the bonding is going to be 100% ionic. Oxygen's the winner. For formal charge, it's not winner take all. For formal charge, we assume it's completely 50-50. 50-50 split. And therefore, they're going to share this evenly. There are 2 electrons in this bond. So one electron goes to the oxygen, the other electron goes to hydrogen, no matter how much more electronegative oxygen is. And so we're going to split the electron density down the middle. Half of it goes to hydrogen, the other half to oxygen. And so that means hydrogen has 1 electron worth of density. If hydrogen has 1 electron's worth of density, well, the hydrogen ends up with 1 electron. Hydrogen's normal valence is 1 electron. And so it's supposed to have 1 electron, it has 1 electron, so it neither came out ahead or behind. It just broke even. So its formal charge is 0. Oxygen is 1, 2, 3, 4, 5, 6. 6 electrons, it's supposed to have 6 electrons, so its formal charge is 0. And this hydrogen's formal charge is 0. So all the formal charges are 0 here. Now, that brings up a question, is oxygen 0 charge or is it -2? What is it? It's neither, it's neither because, the oxygen-hydrogen bond is not 100% ionic, it's not 100% covalent, it's somewhere between 0 and 100%, right? It's in the polar covalent range of bonds, polar covalent. And so it's neither, but, so it's neither of these is accurate, right? And so why do we do this? Clearly this is not 100% ionic and the oxygen does not have a -2 charge. And so why do we even bother with it? Why we bother with it is because, did we have to do any experimental measurement to determine the charge, -2 here? Did we have to do any theoretical calculation using quantum mechanics and the Schrodinger equation? No. And so the reason we use these is because they're very easy to generate. Although they aren't entirely accurate. What would be more accurate? What would be more accurate would be that the charge is somewhere between 0 and -2. If the charge is somewhere between 0 and -2, then it's got some kind of partial negative charge, delta minus, right? And over here, the hydrogen's charge is going to be from 0 to +1. It's somewhere in between there. In between 0 and +1, we'll just call it delta plus. It's not quite a full positive charge, but it's not 0 either. And this one would be delta plus as well here. Let's make this a little bit bigger. Okay, now tell me what delta plus is. What's the number? Is it 0.7, 0.8, 0.9, 0.65? What is it? How much electron cloud is there? See, we don't know without having to do a calculation, quantum mechanical calculation, or measuring the dipole moment. It's not easy. Yes, that would be the most accurate, right? As far as the charge goes on that particular atom, but we don't have easy access to it. And so what we do is for example, we don't compare any of these three, really. You know, we can compare blues with blues and greens with greens, but we don't cross-compare. And so even though the number is not accurate, oxidation states are accurate for ionic compounds because ionic compounds are 100% ionic or close enough to it, right? But pretty poor for covalent compounds. So for example, something that's nonpolar, oxidation states would seem to be very far off, you know. Something like methane. What's the oxidation state of carbon in methane? -4. Here we're going to be way off, but for sodium, what's the oxidation state of sodium and sodium chloride? Oh, it's +1. Oh, that's right on, right? And then so of course it becomes more accurate as it becomes more polar, but still, even though this is way off, you know, this is a nonpolar bond basically, pretty much close enough to 100% nonpolar that we call it nonpolar covalent. Even though this is not anywhere close to ionic, this number is extremely useful. Why? Because we make comparisons. We make comparisons to other carbon compounds. And then we memorize things. You know, we memorize a range of numbers for carbon. And then we see, you know, how do these numbers compare to others? For example, like chloroform or CO2 or CO or whatever, right? And so, yeah, you might say that's not accurate here, it's fairly accurate here, it's somewhere in the middle here, but it doesn't matter. We use the oxidation states as given, you know, and then we compare them, and we memorize some kind of framework for comparing these. Because it's very tricky, you know, -2 on oxygen isn't the same thing as a -2 on carbon. Totally different. You know, -2 on carbon is still electron rich. A -2 on oxygen is not. You know. And so those are oxidation states. Formal charges are a bit easier to deal with because we just look for formal charges as far as the number goes, you know, and then make comparisons there. Most of the formal charges are 0, so having 0 formal charges, that doesn't tell us much. You know, all these formal charges are 0 here, right? It's just when we get a non-zero formal charge, then something pops up. And these delta pluses and delta minuses, we aren't going to assign any numbers unless we do a calculation or we get the number experimentally, something like that. And so when we go back to these structures for bicarbonate, look at the structure for bicarbonate. Something like this. So we made a double bond here. Is that where we had it? Okay, and now everything has an octet. But you look at the formal charges, okay, what's the formal charge on hydrogen here? Split it down the middle, it has 1 electron, it's supposed to have 1 electron. The formal charge is 0. On this oxygen, 0. This carbon, 0. This oxygen, 0. This is -1. This oxygen ends up with an extra electron because it has 1, 2, 3, 4, 5, 6, 7. It's supposed to have 6, so it has an extra electron. Well, that extra electron is no problem because this whole thing has a net negative charge. All the formal charges must sum up to the net charge on the species. And so we got to have a negative charge somewhere, right? And do you guys remember resonance forms? Resonance forms are rearranging the electron density while leaving the atoms fixed. And so one way we can rearrange electron density in this particular structure is we can bring these lone pair into the bond here, but that makes more than an octet on carbon, so it has to kick out this bonding pair and make it a lone pair. And so we can come up with what we call an equivalent structure here, like this, where we have a double bond on the other oxygen here. And this gets converted to a single bond. Okay, normally we just write the non-zero formal charges, so this is negative, and that's going to give us a net negative charge here.
In the fifth semester, we had questions on different types of water molecules. The resonance structures, are they the same conceptually, like the different water molecules? Like that?
What do you mean by different, like hydroniums?
Yes, remember how you asked those questions? Can we have different water molecules? How many different water molecules can we have?
Oh, no, it's different. It's different. You know, it's different because neither of these is correct. You know, if I have a sample of bicarbonate, it's not 50% of the bicarbonates are like this and 50% are like this. I'll talk about it. Actually, there's one more. Let me do the one more before. This is the 3 oxygens. So we formed a double bond on the top one, double bond on the right one. Let's form a double bond on the left one. If we form a double bond on the left one, they'll bring that lone pair here and then kick out this bonding pair out here. So we have some structure like this. This whole thing carries a negative charge. But when we look at this structure and look at the formal charges, we have a negative formal charge on this oxygen, a negative formal charge on this oxygen, and on this oxygen we have a positive formal charge. Does that look good to you? No, this one looks very bad to me. It looks very bad because, you know, why is this oxygen the loser and this oxygen is the winner? Well, either one of those two. You know? And so in other words, compared to this, you know, the 2 oxygens are 0 formal charge. They each have 6 electrons. But now we go here, this one has 5 electrons, this one has 7 electrons. You know, why does this one lose 1 and this one gain 1? And so this is not good. This is unstable. If it's unstable, it's going to be high energy. And so we eliminate this structure here because of the formal charge separation. This is, you know, this would be like trying to take all the electrons off something and put it into a bottle. And so you just leave behind the positive charge. There's a separating charge. Separating charge creates a voltage. Creating voltage takes energy. And that energy is going to destabilize this. And so this one's not a contributor. We don't call it a contributor. Now, a contributor to what? And so normally when people think about resonance forms, you know, they think of things resonating back and forth. So for example, the negative charge would resonate between these two, you know, back and forth, back and forth. And the double bond would resonate here, you know. But it doesn't resonate. In fact, what we have here is the most accurate depiction for this would be called the resonance hybrid, the hybrid structure. Call it hybrid. The true structure for this is a mix of these 2 forms. And so let's take a look at what the hybrid would look like. Let's draw it here. The hybrid structure for bicarbonate going to have a single bond on each of these two oxygens, but the double bond is shared between the two. So I'm going to draw a dash like that. And so rather than having a single and a double, we even it out. If you spread out the electron cloud like this, what we end up with is a 1.5 bond on each, a 1.5 bond. So this will be a 1.5 bond. So now the two bonds are equal. They're both 1.5 bonds, not a single and a double. So it doesn't resonate. It doesn't resonate between single and double. It just stays as 1.5 bond. And the lone pair, there are two lone pairs fixed on each oxygen, and a third lone pair that's spread out over both oxygens. So we'll just spread out this lone pair here. And so the charge that we get isn't a -1, 0, -1, 0, and it just flip-flops, but it's a stable charge, a -1/2 on each. And so the electron cloud on the lone pair is spread out over the two. And so when we sum up the formal charges, it's -1/2 plus -1/2 gives us our net -1 charge here. This is called a hybrid, and this particular hybrid is a 50-50 mix of both resonance forms. Here. That third resonance form is not going to be mixed in to this hybrid structure because it's too unstable. And so this turns out to be a mix of the first two structures I drew there. Yeah, we can eliminate the high energy structures. All right, then tomorrow we'll look at a little bit more complicated